So subject which we are starting here is a digital logic. In case of this subject, we are going to study the modern day computer in the most basic form possible. Okay. So first of all, we should understand what is the topic which we are going to cover here. So the topic initially which we are going to cover is the logic functions and the function minimization. Then we'll cover the combinational circuits. After that, we'll cover the sequential circuit. And after covering the sequential circuit, we'll cover the number system, number representation, the computer arithmetics, and so on. Right? So basically this subject is divided into these four basic parts. So initially we'll start with the introduction to the switching algebra, and with this introduction we'll slowly make a transition towards the logic gates and the families of logic gates. Okay, so first of all we should discuss the basic properties of the switching functions. So the first basic property is idempotency. So what is idempotency? It says if we do x dot x, then it is equal to x, and if we do x plus x, then it is equal to x, where x is a Boolean variable. Okay, so what x Boolean variable means, x can take only two values which can be zeros or 1. So the first one is x dot, right? Dot is also called as AND here. It means if we have an x and this is also x, and we do x dot x, their values can be 0 0 or 0 1, 0 0 or 1 1, sorry. So if we take 0 0, then we will get 0, and if we take 1 1, then we will get 1. Fine. Now if we take x plus x, what is x plus x? X plus x means we are going to do OR. That means we have this is x, this is x, this is x plus x. Their values can be 0 0 or 0 1 or sorry 1 1. Then x plus x will be 0 and 1. Right? So in both these cases, these are equal to x only. If we add 1 to x, right? So what does that mean? That means if this is x and this is the other 1, the x can take a value 0 and 1, and we have to OR x, we have to OR the variable x with 1, therefore this will become 1 only, right? In this way, again here we can say x dot 0 is equal to 0, x plus 0 is equal to x, x plus 1 is equal to x. So this is called as idempotency property. The next one is the commutativity. Commutativity means we can commute them. That means if we do x plus y, then this will be equal to y plus x. In the same way, x dot y will be equal to y dot x. This is called as commutativity property, right? The next property is associativity. Associativity means we can associate the brackets. And what does it mean when I am saying we can associate the brackets? It means we can prioritize the variables accordingly, the operators accordingly. That means if here initially we are doing x plus y plus z, it means that initially we are going to calculate what is x plus y, and then we are going to add it with z, right? Here it is x plus y plus z. That means first of all calculate what is y plus z, and then perform an OR operation between these two. Then perform an OR operation between these two. Here it is having the higher property as compared to this dot. This dot is having higher as compared to this dot because of this opening and closing brackets, right? In the same way here, I should have written like this. This is x plus y dot z, sorry, x dot y dot z should be equal to x dot y dot z, where this is having higher priority and here these are having higher priorities, right? So this is called as the commutativity property. Okay. Next is the complementation property. That means if we add x with its complement, then we will get 1. If we this is OR operator, again this is AND operator. If we add x with its complement, then this will be equal to 0. And the next property is the distributivity property, which says if we do x dot y plus z, then we can distribute this x over y and z, then this will be equal to xy plus xz. In the same way here we have x plus yz, where we have a dot operator between y and z. So we can distribute this x over this y and over this z. So this will become x plus y dot x plus z, right? And the next property is the absorption property, which says if we have x plus xy, where we have dot operator between them, then this will be equal to x itself, right? Now if you see all these operations, you can see they always come in a dual form, or they always come in a pair, right? When I'm saying they always come in a pair, then you can assume, you can imagine it this way. In the case of commutativity, we have two properties here. Associativity, again two properties. Complementation, again two properties. Everything is in a pair. Here it is also in a pair. Here these things are also in a pair, right? So this is in a pair, this is in a pair, right? This is in a pair. Again, we can also give a pair property for this also. That means every switching algebra or every switching expression can be represented into a dual form. What is a dual form? Dual form of an expression, when I'm saying a dual form, it means if we have a function, or you can say an expression can be represented using a function, and we have some variables. Assume the variables can be x1, x2, x3 up to so on xn. We have plus, dot, 0 and 1 as operators, right? We have plus and dot as operator. These two are the operators. These are the variables. Here in this case, these are Boolean variables, and these are the constants, right? Then if we take a dual form of this function, that dual form, assume it is represented by f dual, then it will be equal to, take all the variables as it is, like x1, x2, x3, x4 up to so on xn, and then replace all the plus with dot and all the dot with plus and zeros with 1 and 1 with 0, then whatever expression you will get, that will also be valid. Then whatever the expression you will get, that will also be valid, right? So what does it mean? It means, let us see here. See, in this expression we have x plus y is equal to y plus x, right? Then what is the dual form of this? You take x as it is, you take y as it is, x as it is, and replace all the plus, replace wherever you get a plus with the dot, and wherever you get a dot with a plus, right? So you can replace this plus with the dot, again replace this plus with the dot, and then whatever form you will get, that will also be valid, right? In the same way, again here you can say in distributivity, we have a dot operator here, dot, you can see if we replace this dot with plus with dot, again dot with plus with dot with plus, then whatever the expression we will get, that will also be valid, right? So you can say this expression is a dual form of this, or you can say this expression is a dual form of this. The dual forms also exist. In case of switching algebra, duality is there, right? So in this case also you can see this, we have written x as same, x complement as same, we have changed this 1 to 0, or you can say 0 to 1, and we have changed this addition to dot operator, right? That means a dual form is also valid. In the same way, when we say absorption property, again we can give a dual form. What is the dual form? Take all the x as it is, this is x again, you can take this x as it is, this y as it is, and this x as it is, and then change all the plus with dot and all the dot with plus. Then what you will get? X dot x plus y will be equal to x itself, right? So this is a dual form which is also valid. That means a dual form is also valid, as you can see here. The next form which we need to know is the De Morgan's law. So what is the De Morgan's law? I'll write it here. It is De Morgan's law. What is the De Morgan's law? It says if we have x dot y whole complement, then we can write it as x complement plus y complement. In the same way, if I take a dual form of this, then this will be x plus y whole complement, then we can write it as x complement dot y complement, right? As you can see here again, the dual form is also valid. Okay? So let us try to solve a few questions on this. Let us take this question. It is a very simple question which is asking GATE 2004. You can see here we have a Boolean function which is x complement y complement plus xy plus x complement y. Now they are asking this function is equivalent to which of the following, right? They have minimized this function. Now they are asking this function is equivalent to which of the following, right? So now let us try to solve this. In this case, you can see between these two statements we can take y as common, so it will be x complement y complement plus x complement dot y, right? And here you can see if we do x plus x complement, then this is equal to 1 only, right? Because we are adding a number and its complement which is equivalent to 1, right? So this will be equal to x complement y plus 1 dot y, and 1 dot y is equivalent to y itself, right? So it can be written as x complement y complement plus y, right? Now we can distribute y over these two. We can apply distributivity property here. So this will be equal to x complement plus y dot y complement plus y, which is equal to x complement plus y dot 1. Why? Because this is equal to 1 itself. So this can be written as x complement plus y, x complement plus y. So this whole expression can be written as x complement plus y, which is option number D here, which is option number D here. So option number D is correct. So this is a very simple question which is asking GATE 2004. Now let us take more examples of this kind of simple questions. So this question was asked in GATE 2004. It is a very simple question. Let us see. Let us try to solve this question again. So they are saying we have the function which is a b complement c plus a complement bc plus a b c complement plus a complement b complement c plus a b complement c complement, and it is equivalent to which of the following? It is equivalent to which of the following, right? So now let us try to solve it. Let us try to identify from where we can take something as common. Okay, so BC again a b complement, fine. So now let us take a b complement as common between these two. So we will get a b complement, inside we will get c plus c complement. So we can write it as plus a complement bc plus a bc complement plus a complement b complement c, and this is equivalent to saying 1. So it can be written as a b complement plus. Now can we take something as common between these three? Let us see if we can take something as common. Here if we take a complement c as common, then we will get a complement c, inside this b plus b complement plus a b c complement, which is equivalent to saying a b complement plus a complement c plus a b c complement plus a b c complement. Now let us try to see if we can distribute something over them. If we take something as common, let us say we take a as common between these two, then it will be a as common, then it will be b complement. It can be written as b complement plus b c complement plus a complement c, which is basically again distribute b over here. So it will be b complement plus b dot b complement plus c complement plus a complement c. Here this is equivalent to 1, so it will be a dot b complement plus c complement plus a complement c, which is equal to a b complement plus AC complement plus A complement C. So this is matching the option number B here. So option number B is correct. So as you can see, it is a very simple question. It will just take a little bit of practice to solve these kind of questions, right? So we'll take more examples here. Now let us try to minimize these Boolean expressions. So it is saying A complement B complement C plus BC plus AC. Let us see if we can take something as common between them. Take C as common, then it will become A complement B complement plus B plus A dot C. We have taken C as common. Now you can distribute B over this. You can distribute this B over this. Then it will become something like this. A complement plus B dot B complement plus B plus A dot C, and this will become 1. So it will become A complement plus B plus A dot C, which is equal to A complement plus A plus B dot C, and this is equivalent to saying 1, which is equal to 1 plus B dot C, and this is equivalent to 1 again, so it is C dot 1 C. So it is a very simple question again. Now we try to solve this one. We have x plus y dot x complement dot y complement plus z complement का whole complement plus x complement y complement plus x complement z complement, right? So let us try to solve it. Again here we can apply De Morgan's law. It can be written as x plus y dot apply De Morgan's law. So it will be whole complement of x complement dot y dot z whole complement plus x complement y complement plus x complement z complement, which is equal to x plus y. And this you can apply De Morgan's law here again. So this is a bracket, this is a complement here, which can be written as x complement plus y dot z complement plus x complement y complement plus x complement z complement. I'm sure you have done this before. It is very simple. If you feel any problem here, just let me know. It can be written as x plus y dot x plus yz plus x complement y complement plus x complement z complement. It can be written as you can distribute over here. So it is x dot x plus x dot yz plus y dot x plus y dot yz plus x complement y complement plus x complement z complement. It can be written as x itself, and so it will be x plus xyz plus xy plus this is yz plus x complement y complement plus x complement z complement. Now you can take these two. We already know that x plus xy is equal to x itself, which is the absorption law. So it can be written as x plus xyz plus yz plus x complement y complement plus x complement z complement. And you know you can take x as common here, so it will be x 1 plus yz plus yz plus x complement y complement plus x complement z complement, which is equal to x, this is equal to 1 plus yz plus x complement y complement plus x complement z complement. You can distribute x over here, you can distribute x with them, so it will be yz plus yz plus x complement x plus y complement plus x complement z complement, which is equal to yz plus this is equal to 1 x plus y complement plus x complement z complement. You can distribute x with them and you can distribute y with this. So what we'll get again, we'll get something like this. If you distribute y with this, then this will be equal to y plus y complement dot z plus y complement plus this is x plus x complement dot x plus z complement, which is again equal to, this is equal to 1, so it is z plus y complement plus this is equal to 1 plus x plus z complement. Again you can write it as x plus y complement plus z complement, and z plus z complement is equal to 1, so it is x plus y complement plus 1, which is equal to 1 itself, right? So you can minimize the above Boolean expression like this. It is so simple to, so simple. You just need some practice to solve this kind of questions, and as you can see, there are a lot of this kind of questions are generally asked in simple 1 mark question gate examination, right? So now let us move on to the next section. What are Boolean functions? What are Boolean functions? What are Boolean functions? Boolean functions. For example, I can represent a function like this. If we have f of x comma y comma z, it is equal to xy plus z. We can represent a function like this, right, where x, y and z are the variables. What does it mean? Let us try to draw it. We have 3 variables here, which are x, y and z, x, y and z, and there is a function f which is representing x comma y comma z, which is equal to xy plus z, right? So what are the combinations of x, y and z? They can be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. These can be the combination, and let us categorize them like this. If I am drawing the line, does not mean that I am dividing them like this, just for clarity, that we don't make any mistakes here. So this function is representing xy plus z, xy. This function is true only when x and y both are true or z is true. You can read it like this. It is x dot y plus z. That means if this is true only when x and y both are true or z is true. So what are the places where x and y both are true? These are the places where x and y both are true. So here this function will assume a value 1. So it is 1 and 1. And when it is not true, then z should be 2, or you can say z should be 1. So z is 1 here, 1 here and 1 here, and all the other places the function will assume a value 0. The function will assume a value 0, right? So in this function you can see a Boolean function is like a combination of these variables, where at some places this function assumes a value 0, at some places this function assumes a value 0, and at some places this function assumes a value 1. Now we can represent this place like this. Here it is 0, 0, 1, it is 0, 1, 1, it is 1, 0, 1, it is 1, 1, 1. Or we can also represent it like this: 0 with x complement, y complement, z, 0, 1, 0, 0, 0, 1, 1 is x complement, y, z. It can be represented as x, y complement, z. It can be represented as x, y and z. The same function can also be represented like this. The same function, which is f of x comma y comma z, it can also be represented like this: x complement, y complement, z plus x complement, y, z plus x, y complement, z plus x, y, z plus x, y, z. So this function and this function, both of them are representing exactly the same thing. Both of them are representing exactly the same thing. But what is the difference between this form and this form, right? So this form is called as the sum of product form. It is sum, we can say sum of products, and this form is generally called as canonical sum of product. Canonical sum of product, right? We can also show a product of some form. Product of some form. Product of some form. What is a product of some form? So in case of product of sum, we have to find out where the function is assuming a value 0. What are those places? At this place the function is assuming a value 0. At this place the function is assuming a value 0. At this place the function is assuming a value 0. Right? Is there any other place where the function is assuming a value 0? Did I forget any combination? I forgot to write one combination here. This is the combination, right? So it is x, y, z complement. So we can add one more combination here. It is plus x, y, z complement, right? And if I say we have product of some form, in case of product of some form, we take a value which is non-complemented for zeros. So it can be written as x plus y plus z. It can be written as x plus y complement plus z, and it can be written as x complement plus y plus z. So product of some form can also be written like this here. It is x plus y plus z dot, here it is x plus y combination y complement plus z dot, it is x complement plus y plus z, x complement plus y plus z, right? So these are the two different forms. This is the sum of product form and this is the product of sum form. So what is the difference between these two forms? Why it is called as the sum of product? The sum of product. Sum of product means you can see it is a product term, it is a product term, again it is a product term, again it is a product term, and we are taking the sum of the product terms, the sum of the product term. This is a sum term, right? Sum of the product terms. And here you can say it is a product of some form. That means we have the product here, and this product is of the sum. This is the sum, this is the sum, this is the sum, this is the sum, and this is the sum, this is the sum. So it is a product of sum form. So what is sum of product form is the combination of these variables, which is x complement y and z. They take exactly true form only for exactly one combination of these variables x, y and z, right? But I'm saying it means that, for example, if you take this term, this term is x complement y complement z. This term will only be true only if we pass 0 here, 0 here and 1 here. If you pass any other value of x, y and z to this term, then this term will never be equal to 1, right? So we have to find out what is the exact combination of these values where this term will assume a value 1. So that is what is the exact combination, what is the exact combination of the values where this term assumes a value which is 1, right? And in case of product of some form, we have to tell what is the exact combination, what is the exact combination of values which we can give for which the term assumes a value 0, for which the term assumes a value 0. Here we are trying to find out for which the term assumes a value 1, and here we are trying to find out for which the term assumes a value exactly 0, right? These are the sum of product and product of some form. Now let us write. I'll dictate here and try to follow with me. Try to write in your notebook. So write down what is the canonical form first. Canonical form. A product term. Write it down. A product term which contains each of the n variables, as factors, either in complemented or uncomplimented form, is called as a minterm. Is called as a minterm. For example, here we have each of these variables in complemented and uncomplemented form, and this term, all these terms, this term is called as a minterm. It is also called as a minterm. This is also called as a minterms, right? This is also called as a minterm. This is also called as a minterms, right? And what are literals here? The occurrence of every variable is a literal, right? So this is one literal, this is one literal, this is one literal, this is one literal, and so on. So how many literals are there? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 15 literals here. There are 15 literals here. In this function, how many literals are there? 1, 2, and 3. So there are 3 literals here. In this expression, how many literals are there? There are 9 literals here. 9 literals here, right? So you can say a minterm gives the value 1 for exactly one combination of variables, right? You can see here this minterm is assuming a value 1 for exactly one combination of variable. This minterm is taking a value 1 for exactly one combination of variable, and here this is called as a max term. It is called as a max term. It is a max term. It is a max term. It is a max term. These terms are assuming the value 1, 0 for exactly one combination of variables, right? So we have a minterm and we have a max term, right? So you can say the minterm is, this minterm will assume a value 1 for exactly one combination of variables, and these max term will assume a value 0 for exactly one combination of the variables. And the sum of all minterms of the function f, for example here we have the function f, you can say the function f, again write down the sum of all minterms of the function f, the sum of all minterms of the function f for which the function f assumes a value 1, for which the function f assumes a value 1 is called as canonical sum of product, is called as canonical sum of product or disjunctive normal form, is called as canonical sum of product or disjunctive normal form, right? So there is a small difference between sum of product form. It is also called as SOP, by the way. So what is the small difference between sum of product and the canonical sum of product? In case of sum of product, it is not necessary that we have every minterm have to contain all the combination of the variables, right? For example, in this minterm z is missing, and in this minterms x and y are missing, right? So in case of canonical sum of product, every minterm in every minterm will be having all these 3 variables which are there in the function. We will be having all these 3 variables which are there in the function, right? And this is a canonical max term. So what is a canonical max term? It says if we have a function which is f, x, y and z, then all the max terms will be containing all these variables. All the max terms will be containing all these variables. Okay, so now write it down. So write it down, the definition of canonical product of sum. Definition of canonical product of sum: a sum term which contains each of the n variables, for example here we have each of the n variables as factors either in complemented or uncomplimented form is called as a max term, or uncomplimented form is called as a max term. For example here this is a max term, right? And the max term gives the value 0. Next point, the max term gives the value 0 for exactly for exactly one combination of variables. The max term gives the value 0 for exactly one combination of the variables. For exactly one combination of the variables. Write the next point. The product of all max terms, the product of all max terms for a function f, the product of all the max terms for a function f for which the function assumes a value 0, for which the function assumes a value 0 is called as canonical product of sum, is called as canonical product of sum or conjunctive normal form, or conjunctive normal form. See, here in this case we have this canonical product of sum. Canonical product of sum is also called as conjunctive normal form, conjunctive normal form, and this is some product of sum, and this is sum of product form, which is also called as disjunctive normal form. Disjunctive normal form. We have disjunctive normal form, right? So canonical sum of product is disjunctive normal form, and canonical product of sum is also called as conjunctive normal form. Fine. If you have any doubt in this, you can always ask me or email me for this. So go through this, process this information. If you feel any doubt, just let me know.